So the talk will be in voice, but I'm the only one speaking, at least during the main talk. I do not look at the local chat. So if you have any questions, save them for later. And when you do ask questions, type them in local chat with word question in caps preceding so that I can recognize them, like this. All right, let's begin with this. Again, welcome everybody. Thank you for coming. And my name is Djorgovski, or Curious George here. I'm a professor of astronomy and data science at Caltech, and I've been working on cosmology and related matters for a long time. So today I'd like to tell you more about dark matter and dark energy, which are probably among the most outstanding puzzles of physics today. And what I'd like to do is first tell you how do we know they're there, what do we know about them, and what we don't know about them yet. And I'll be happy to answer any questions you may have at the end. So these are, as I mentioned, among the most outstanding, if not the most outstanding problem in physics. And solving them will almost certainly expand our understanding of the universe in some way. Because that's how it usually happens, right? Some phenomenology is observed that is not easily explained by the existing physics or other knowledge, and its resolution leads to further progress. Now, we do know that these two exist through their gravitational effects. They may not be visible, that is, they do not interact with electromagnetic radiation, but they very much do have gravity and interact with the rest of the universe through gravity. And many people have tried to explain both of them. Literally thousands and thousands of papers have been written. There is no compelling explanation yet. We think we understand dark matter a little better, dark energy, not at all. And I'll tell you a little more about it. So to give you just a couple examples, historically, how that came about. First, say Kepler's laws. He found that planets go on elliptical orbits and have constant sectorial velocity, and there's correlation between distance from the sun and their period. And that was in the early 17th century, but it took Newton with his theory of gravity to actually explain these laws. And Newton's theory of gravity was a great conceptual advance that explained not just Kepler's laws, but also any gravitational effect from falling apples to the moon going around the Earth. Later on, in the early 20th or late 19th century, there was an attempt by physicists Michelson and Morley to measure the speed of ether, because they thought the electromagnetic waves are propagating through this invisible fluid that permeates everything called the ether. And so if that's the case, the speed of the light would vary in the direction, from the direction the Earth moves to the orthogonal one. And they set up an experiment to measure that, and they found there was no difference whatsoever. And that was very puzzling, because everybody was convinced that there is such a thing as ether. And what was the explanation of this? Well, Einstein's special theory of relativity was pretty much formulated to explain this. It also explained some important questions about electrodynamics. And so that was another major conceptual advance. In fact, in, I think, actually year 1900, famous physicist Lord Kelvin said that, well, physics is pretty much a done deal, except there are these two little clouds in the horizon. And one of them was failure of the Michelson-Morley experiment, which then led to theory of relativity, and the other one had to do with the black body radiation, which led to quantum mechanics. So something like that may happen again. All right, so I'll start first with why we think this is so important. This pie chart shows you what we now think or know is the composition of the matter and energy in the universe. And just shy of 70% of the total mass energy, and by the way, remember E equals mc squared, meaning matter and energy are equivalent, is this new mysterious dark energy. then another 27 or so percent is the dark matter of the composition we do not know, but what we do know is not the kind of matter that we know about, atoms and particles we know about. And then another 4.5% is matter that we actually do know, and only 0.5% is the stuff we see, stars and gas in galaxies. The remainder is a form of hot gas between galaxies. But the upshot is that we do not know what 95% of the universe is made of. Now, you can look at that as a scandal, or you can look at it as a great achievement because we figured this out just sitting on planet Earth. And this is something that affects the entire universe. But it's an obvious challenge, and as I said, it'll probably lead us to some new discoveries. So let's first start with basic gravity, Newtonian gravity. What was shown here in picture is the globular star cluster. Actually, Newton thought that such things could not exist because these stars are all attracting each other through gravity, and what's to stop them from all just falling to the middle and smushing and maybe making a black hole or whatever? And the answer to that is they have kinetic energy. They move around, and their speeds prevent them from all falling down to the same point. Now, if there was no gravity, those speeds also mean the cluster would just fly apart. There'd be no such clusters. And that basically means that objects that are bound by gravity, whether it's star clusters or galaxies like the Milky Way or solar system, have to be in a form of a dynamical equilibrium. Now, don't freak out. This is high school physics, or at least if you went to high school not in the United States. And it says that basically an equilibrium is when you have forces balancing each other, or the balance between kinetic and potential energy. Kinetic energy is from the motions of things. Potential energy is from something like gravitational field, and they have to balance. So in each star is moving at some velocity v, has a little mass little m, and its kinetic energy is the simple formula, A equals mv squared over 2. Potential energy for things in gravitational field are Newton's gravitational constant times the same low mass of star times the mass of the rest of the cluster divided by its effective radius. Now, those two need to be balanced, and in fact, potential energy has to be factor 2 larger to within a sign in kinetic energy. You put these two equations together, and you can see that if you can measure velocities and the size of cluster or galaxy or whatever it is, you can compute its mass. This is how we pretty much know all masses in the universe, starting from stars all the way to the universe as a whole. So this is a fairly well-established thing. You don't need theory of relativity for this. This uses just Newtonian mechanics, and there's no doubt about it. Okay, so in 1933, Fritz Zwicky, who was the original mad genius of Caltech, is his picture, who came up with all manner of really important discoveries and suggestions, including understanding what supernovae are, predicting neutron stars, how gravitational lensing can be used to study the universe. He was also a rocket pioneer, etc., etc. He did the exact experiment that I just shown you, but instead of a globular cluster, he looked at galaxies in the coma cluster of galaxies, which is about 300 million light years away, and looked at their velocities, computed radius, figured out that the mass that's required to keep the cluster together is about 400 times what we can see in visible light of galaxies. And amazingly enough, that's pretty much exactly what modern measurements show. And even his data were vastly inferior. Another astronomer, Sinclair Smith, did the same thing for the Virgo cluster galaxies, the nearest one to us, and pretty much got the same result. But everybody ignored this, even though Zwicky really is the discoverer of the dark matter. People sometimes credit Vera Rubin by that, but that's not true, and Vera never claimed it. she convinced people there is such a thing, or rather her measurements convinced people there's such a thing, but it was Zwicky who discovered it. And so, Zwicky was crazy. He said all kinds of stuff that wasn't true, so people ascribed this one as well. Because what can possibly be this invisible mass? Well, in the early 70s to mid 70s, instruments got so much better, and astronomers, including Vera Rubin and her collaborators, started measuring rotation curves of spiral galaxies, where the rotational speed is what keeps them from collapsing at the same point. And her result, and those of other astronomers working at the same time, especially radio astronomers, notably Ken Freeman, who does not get enough credit that he deserves, found that indeed this is common. These galaxies are spinning way faster than you expect from the mass that they contain invisible stars and gas. And at the same time, theorists were coming up with reasons why such a thing should exist, both in terms of explaining the large-scale structure in the universe and also the stability of spiral galaxies. So here is Vera sitting on her plate measuring machine. People were taking photographic spectra back then. And what's shown here is the actual observed rotation curve, which means circular velocity as a function of radius for nearby spiral galaxy M33. And the dashed curve shows what you would expect if there was no other mass than just what you see in stars and gas. So galaxies get dimmer as you go out, and so at first, as you go out in radius, the speed increases because there is more enclosed mass, and then turns over and slowly falls off. But that's not what happens. What happens is that it kept going up, and at one point flattens out, and large distance it kind of falls back down yet. But there is huge discrepancy between what you expect and what's actually measured. And that tells you unambiguously that there is an extra mass component that you're not accounting for, which we now know is the dark halo. So how does this work? All right, so these galaxies, as I said, are spinning around their axes. Most of the kinetic energy is in that rotational motion, very little bit in random motions of stars. And in something like that, you have to balance the centrifugal force from things going in a circle, it's pulling them out, with centripetal force, which is just the gravity from all the mass within that radius. And those two have to be equal, otherwise the galaxy will either collapse or fly apart. So what we see then is that there is way more speed than you'd expect from what you see, and if you subtract what you expect from stars and gas from what's actually observed, that tells you that there is some mass component that is also concentrated towards the middle of the galaxy, but declines much slower in its density than visible light, otherwise it will be indistinguishable. And so that is now known to exist in every galaxy, and it's the first safe signature of dark matter halos. Now, that's not just the spiral galaxies. Elliptical galaxies don't spin very fast. They are supported by random motions of stars, just like globular clusters are. But in addition, they also have gas. And in clusters of galaxies, where again, galaxies are zipping around with some speed that is sufficient to keep them afloat, so to speak, there is also copious amount of hot gas, about 10 million degrees Kelvin. And that gas, that's that hot, emits mostly in X-rays. And so that's very easily observed with our X-ray satellites, and it's totally ubiquitous. Now, essentially what we're doing here, we're using galaxies as test mass particles in potential well of the entire cluster. Or we can use protons and electrons, because all of the gas is ionized, also as the test mass particles in the same gravitational potential. So they both have to produce the same result. And if you convert velocities of galaxies, which are typically of the order of several hundred kilometers per second up to maybe a couple thousand kilometers per second into the equivalent temperature, because heat is also a form of kinetic energy, you get about 10 million degrees. So that agrees perfectly. And we now know that elliptical galaxies and clusters of galaxies have the same amount of dark matter. And in fact, what we observe in X-rays and through motions of galaxies and clusters is pretty much exactly what Zwicky has found. But there is more than that. And this has to do with gravitational lensing. Now, gravitational lensing is a direct consequence of general theory of relativity. Well, Einstein, among other things, predicted that masses would bend light rays that go around them. And if you line up things just right, then you can magnify objects behind large masses, and you can also distort their shape. And this is, in fact, how general theory of relativity was proven by Eddington in 1919. They saw that stars behind sun during solar eclipse are not where you expect them to be when sun is not in the field of view. And pretty much demonstrated that general relativity is right, because it was a highly non-trivial prediction. Well, it works with clusters of galaxies because each of them has approximately 10 to the 15 solar masses worth of stuff. That's a lot of mass. And then galaxies far behind this cluster will be magnified and distorted. And the picture on the left shows an image from actually James Webb Space Telescope, where they pointed to a rich cluster of galaxies precisely for this reason, because the gravitational lens essentially gives them an extra magnification to aid an 8-meter or 6-meter telescope in space. So this is now well established. If you now analyze these distortions of these little arclets of images of background galaxies, you can model this to find out exactly how much mass is needed to cause this and how is it distributed. And amazingly enough, even though this is completely different effect, different physics, different way of measuring it, it gives you exactly the same result. This is why we believe that this is true, because you measure it in many different ways and completely independent ways, and you get the same number. So that is pretty much why everybody agrees. Now, it doesn't have to be clusters of galaxies. It also works for individual galaxy halos. And so here is an example of an individual galaxy acting as a gravitational lens. This is a picture from Hubble Space Telescope. And you can see this blue ring, which is an image of a background star-forming galaxy that's now been distorted into almost a full ring around the deflector. That's called the Einstein ring. And when you analyze that, you again get exactly the same amount of dark matter needed as you get from rotation curves and such. So I'll say with this, what we could count establishment of this missing, well, not missing because, we know it's there because of gravity, but invisible mass that's ubiquitous in galaxies and clusters of galaxies. But there is more. Here is something that was kind of interesting, that clusters of galaxies which contain dark matter, visible light galaxies, and X-ray gas sometimes collide and merge. So when they first encounter each other, they come accelerated by the mutual gravity. They actually cannot pass through each other because atoms in space and galaxies are separated much further apart than their sizes. And so they do not collide. They just kind of zip through each other, and then eventually they bounce and mix and make a new, bigger cluster. But after the first pass, galaxies and dark matter are all following the trajectory of initial pass-through, but not the gas. The gas clouds collide and cause the shocks, and so the X-ray gas from the two clusters kind of stays in the middle. And that's exactly what you see here. In fact, you see a bow shock on the one on the right. So there are a bunch of more cluster collisions that we know now that do this. And the only way to understand this is the presence of the non-collisional dark matter, which here is indicated in false colors in blue. And we know that's there because of the gravitational lensing that those clusters provided. So this is yet another piece of evidence. A more important but difficult to explain in this talk is evidence from cosmology, and specifically from studies of cosmic microwave background, which is the afterglow of the Big Bang, when the universe was fully ionized, and it was released when the universe was 380,000 years old. Now it has these little fluctuations in it, which are parts in a million that have been studied with great precision. And studies of microwave background fluctuations have yielded us by far the most precise measurements in cosmology of anything, including a requirement for the existence of dark matter and the existence of dark energy, and exactly in the same amounts as observed closer to us. So this is actually where pretty much most of the modern cosmology studies are happening. And wait, there is more. It turns out you couldn't make galaxies or clusters if there wasn't dark matter. Our understanding of it is that dark matter halos, they collapse first, even before the visible stuff, baryons, have a chance to do anything. And they form gravitational seeds, potential wells into which normal stuff falls on later on and makes stars and what have you. And if you go through the numbers and formulas and you run simulations like these, you find out that that's exactly right. And if the dark matter wasn't there, galaxies and clusters would not have time to form, may never form. Or if they do, it will take much, much longer than 14 billion years. That's the age of the universe today. So that is actually a very compelling argument from theory has been well proven, demonstrated, and it just supports everything else. So everything, theory, observations from all different ways, gravity, everything comes together and gives you the same result. Well, some people propose, well, actually there's no dark matter. You just don't understand gravity. You have to tweak the gravity. That's pretty much certainly not correct. Our theory of gravity is general relativity, which reduces to Newtonian gravity in the limit of weak gravitational fields and speeds much slower than the speed of light. And GR is probably the best tested theory, physics theory ever, and it's passed all tests people thought of from laboratory through stars and pulsars and galaxies and black holes and gravitational waves, the entire universe, with exact right answers. And it also made predictions that were totally non-trivial, such as existence of gravitational lensing, the expansion of the universe, the existence of black holes, the gravitational waves. It is a spectacularly well-established theory of gravity. So if you want to come up with a different theory of gravity, you have to repeat that success. You have to have your new theory be consistent with what we already know, and then maybe push to some deeper understanding. There is no such theory. An example is one that was popular early on, and today there may be, well, there are fewer proponents than fingers on one hand, and it's called modified Newtonian dynamics, or MOND. It was proposed by a physicist named Mordecai Milgram in '83, where rotation curves were still relatively fresh. And I said, well, why don't we change Newton's second law, the one that connects acceleration with force? And it changes that completely ad hoc, adds a new parameter. There is no physics behind it whatsoever. It was inconsistent with general relativity. It made actually wrong predictions. People have shown that if this was true, the clusters of galaxies would fly apart. It made no good predictions ever. And some people just can't admit they've been wrong, so they still stick to it. But I would say 99.999% of all astronomers, cosmologists think this is bunk. So there are serious theories of modified gravity, but they usually pertain to early universe and dealing with dark energy and whatnot. None of them has been successful or seen as a viable candidate for what we know. There's just some particles that we don't know yet, and they have gravity, they just don't interact with light. Okay. So, what are we doing to find out? Astronomical observations are what we know most about dark matter. I didn't even tell you everything. I mean, for example, we know it's made of some kind of particles that are fairly massive, much more massive than, say, protons and neutrons. And we know that because the way the structure of the large-scale structure in the universe will be different. And so there are two additional ways in which we can look for it. One is direct measurements, and several groups are doing this. And even though the dark matter particles would not interact with regular matter electromagnetically or through nuclear forces or anything like that, they could interact mechanically. You can have a dark matter particle bump into some atom and give it some kinetic energy, and that could be observable. So what people do is they build these ultra precise colorimeters and put them a few kilometers under the ground in deepest mines they can get to. They do this to shield from cosmic rays, which could do the same thing. So if you put a couple kilometers worth of rock between you and cosmic rays, that helps. And the idea is to look for a signature of small deposits of kinetic energy that can be analyzed. There has been no convincing detection today. But it doesn't mean there won't be, because these are second most precise measurements in all of physics today. The most precise ones are gravitational waves. And this can well happen. So people who are doing this are sort of narrowing down the observable parameter space in terms of masses of particles, cross sections, and stuff like that. And they excluded a whole bunch of theoretical suggestions, but there is still some space remaining to be explored. The other way is through accelerators, like the Large Hadron Collider in Geneva, but so far that didn't pan out. They just simply haven't found these particles. Let's talk about now dark energy, which first made an appearance in the form of cosmological constant. Now, here is your one slide understanding of general relativity, and don't freak out about this equation. I just want to show you what's equal to what. But one way to summarize general relativity is that presence of mass or energy determines geometry of space. And geometry of space tells matter and energy where to go. And if you solve this in self-consistent fashion, that's what Einstein equations are. So what's shown here is a so-called tensor equation. You don't really need to know about this. And it's actually a shorthand to write down 16 partial differential equations, 4 by 4. They're 4-dimensional space-time. So the thing on the left is description of the geometry of space-time. Right is the description where mass, matter, and energy are, and how they work. And there is a new term which came out of general relativity, that's some constant, which usually noted with Greek letter lambda, times the metric tensor. So this is very much a prediction of the general theory of relativity. But theory doesn't tell you what the constant, or if it's plus or minus or anything like that. It is a signature of new physics, right? But on the other hand, this theory doesn't tell you what Newton's gravitational constant ought to be either. And in fact, quantum mechanics doesn't tell you what Planck constant ought to be, and so on and so forth. So theories of physics we have today use fundamental constants, but they don't predict their value. Anyhow, this is what Einstein got. And this was done before people knew that the universe was expanding. So what Einstein did, having nothing better, was to set the value of this constant to exactly balance the self-gravity of the rest of the universe and to stop it from either expanding or collapsing, because back then in 1915, that's what they thought. The universe is static. And so in 1920s, when Hubble found the universe is expanding, well, that was that. And Einstein apocryphally says that this was the greatest mistake of his career. Here he is in a stage photograph on Mount Wilson Observatory with Hubble and Walter Adams, another astronomer, looking over his shoulder, pretending to see something through an eyepiece. And of course, that's not how it works. So Einstein referred to it as the greatest mistake of his career because he failed to predict the expansion of the universe, which would have been probably the greatest prediction anybody could make. He did plenty of good stuff, but this would have been like a really crown achievement. And he, introduced this little fudge to prevent the universe from expanding and regretted it. It turns out that Einstein's solution for this was actually unstable. It doesn't work. It did not mean that he thought that coming up with cosmological constant was the greatest mistake of his career. It's there in the theory. He didn't make it up. It just comes out in the equations. But this was misunderstood. And for decades thereafter, for some reason, people thought the cosmological constant is something that really is wrong. It must be zero, because what else could it possibly be? Well, I'll come back to that. Now, first to notice is that this new energy, if it's constant in time, is what we call cosmological constant. But in principle, it could be changing in time. We just don't have physics tell us how much. Is an energy that permeates all of the space, physical vacuum. Now, back in Einstein's days, vacuum was vacuum. There wasn't, vacuum means there's nothing. Okay. Not so in quantum physics. Vacuum is very much alive in a field with virtual particles and energy and so on, but that came later. And the really interesting part of this is that the universe expands. That means there are more cubic centimeters all the time, but every one of them has the same level of energy density. No other form of energy that we know does this. All other forms, particles, photons, they all get diluted as the space expands. Not this one. And that is probably a hint. It's probably an inherent property of physical space-time that we do not understand yet. It's not like energy or kinetic energy or potential energy. But nevertheless, it is an energy. And since energy and mass are equivalent, E equals mc squared, it is also a source of gravity. Now, it also corresponds to a negative pressure, or it increases with distance, unlike normal gravity that decreases the square of the distance. And so it's like an elastic energy. If you have a spring and you stretch it, the force, elastic force, is proportional to the stretch. So you can think of it as an elasticity of physical vacuum. But it only appears, or rather it's only really detectable on cosmological distances. It's totally irrelevant when sizes of galaxies are smaller, or Milky Way or something. Right? Well, people are reluctant to admit that there is a new constant of nature, and I don't understand why, because we had plenty of others. Newton's gravitational constant, speed of light, which is also a property of space-time. Elementary charge of electrons, Planck constant. So why not one more? Because general relativity was a fundamental new theory, and why not have its own fundamental constant? You can think of it as another phase of gravity. It's like electromagnetism unifies electric and magnetic phenomena into a single phenomenon called electromagnetism. And that in itself is then unified with nuclear weak force, and it's called electroweak interaction. Well, gravity may have two phases too, and one is attractive one, the one that we know since Newton's days, and there is this new one, which really only operates on cosmological scales. Well, here a key idea, again, about physical vacuum was due to Soviet physicist Yakov Zeldovich. Here is his picture. He was one of the two fathers of the Soviet hydrogen bomb. The other one was Andrei Sakharov. Sakharov couldn't keep his mouth shut and ended up in an exile and so on and so forth. Sedovich was smarter and he kept his mouth shut and they let him be a phenomenal leader of physics in Soviet Union, but he knew what was going on. Anyhow, as I mentioned, quantum theory tells us that physical vacuum is not empty, that the virtual pairs, virtual not in the sense that Second Life is the virtual world, but pairs of, say, particles and antiparticles that appear and disappear very quickly. They satisfy so-called Heisenberg's uncertainty principle, but very briefly they're there, and they do exert some gravity or some energy density. And that's actually been measured indirectly through so-called Casimir effect, but that's a whole another story. So quantum theory tells you there is going to be such a thing, but it does not give us yet means of computing exactly how much, because we're still lacking quantum theory of gravity. The upshot is this will be essentially energy density physical vacuum and will be exactly like cosmological constant. So even though we can't compute how much it really is, people did try. And that led to the worst scientific prediction ever. And it goes like this. There is so-called Planck system of units, which is like, okay, nature doesn't know what meters and centimeters and feet and miles are about, but nature knows what fundamental constants are. So if you can make combinations of fundamental constants that have dimensions of time or space or energy or mass, those would be sort of natural values for those things. And for space, it would be something like 10 to the minus 33 centimeters. For time, it would be 10 to the minus 43 seconds. And the density on Planck scale will be something like 5 times 10 to the 93 grams per cubic centimeter. But the observed energy density of dark energy is 123 orders of magnitude less. Oh, and so physicists call this a fine-tuning problem because somehow they thought it starts with 5 times 10 to the 93 and it all cancels except for one part in 10 to the 123. Well, I think that's bogus because this is not a theory. This is just hand-waving about some units. And if you apply this to the entire universe, you say, well, the whole universe has got to be density of 10 to the 93 grams per cubic centimeter, and the whole universe would last 10 to the minus 43 seconds. So why ignore that, but ascribe it to dark energy? Right? Well, okay, so they couldn't think of actual value, so well, the other possible natural value is 0. Although it could be anything, doesn't have to be 0. It's, like physics students say that when you're doing tests and you have no idea what the answer is going to be, the best thing to write down is 0, because then you don't have to worry about the units. Well, somehow people took this seriously and they just decided a priori, oh, it's got to be 0 because we can't figure out what it is, and they just carried on. But the right way to do it is, of course, to actually measure it. And that's what we've done. So let me tell you about cosmological models that are really a direct consequence of general relativity that describe how exactly is the universe expanding. And they're described by so-called Friedman equation, which is one of Einstein's equations. And I'm not going to write it down for you, but it looks kind of like this. It tells you what the expansion rate of the universe is at some given time. And it has terms that do to matter energy density, because gravity will tend to slow down the expansion. It has terms that has to do with space curvature. And it has this new cosmological constant term. And so these models are usually plotted like this. There is separation between any two unbound points, so co-moving separation, versus time. And they say, well, some universes will expand forever, Others that have too much gravity will eventually slow down and recollapse back in the opposite of Big Bang, called Big Crunch, and relax. That's not what's going to happen. So as far as we know, universe is going to expand forever, which is of course a long time, and all kinds of stuff can happen. But anyway, this is the way we can quantify expansion of the universe as a function of its contents. And these models were first worked out by Friedman and Lemaitre in 1920s and 1930s. Yeah, 1920s. And they're called Friedman-Lemaitre models, and we use them today. Okay, so let me just tell you a little more. How can we then use this to find out what's inside the universe? So y-axis here is this co-moving separation. So think of it, two galaxies far apart, sometime later they'll be further apart. And that turns out to be directly measurable through so-called cosmological redshift, because as photons travel through space, they get stretched by the same amount, and we can measure that directly through spectral gas. The x-axis is time. Now, unfortunately, galaxies don't carry clocks with them, but instead of time, we can substitute distance, because multiply time by the speed of light, you get the distance. So you measure relative distances between galaxies at different redshifts. Okay, so that is how you can test which model we live on, and you can only do it for the portion of the curve that's in our past. But you will predict what the universe will do in the future. Okay, so this is essentially what observational cosmology is really all about, and there are many different ways by which we can do this, which I will not go into any details. Now, cosmological constant was kind of in an exile, like Andrei Sakharov, for decades because of the prejudice. And even though physicists, well, astronomers, not physicists, were saying, well, wait a minute, we don't really know what it is, and there's some hints that could be something, that was kind of ignored until 1998. And there, more or less the same time, there were two very important observational advances. One was measurements of the cosmic microwave background fluctuations that I referred to earlier. And among other things, they give you possible values of the matter density and vacuum energy density, and they're correlated. Never mind why. And the line that's at minus 45 degrees is corresponding to the flat universe. So what microwave background measurements told us is that universe is very close to flat, but we knew that universe density is about 1/3 or quarter of what's needed to make it flat, and so the rest had to be made out from vacuum energy density. But then specifically, another group, actually two groups, measured distances to supernovae far away, and that allows you to put distance and redshift points on those diagrams, and those error ellipses are orthogonal to microwave background, and together they kind of nail things down that the universe is flat, means it has this exact critical density. About 30% of that will be matter, and 70% will be dark energy. And then everybody really bought into it. Those measurements got a lot better since. What I'm showing you here are not the original plots, but more modern ones. But, you get the idea. Well, that was recognized with the Nobel Prize in Physics in 2011. There were two groups. One was led by Perlmutter and Rees, and another one by Brian Schmidt, and they shared the prize, and this is the Nobel citation. Well, I can tell you a lot more about them, but I'll tell you about Brian Schmidt. He is the nicest guy ever. He's an astrophysicist. He lives in Australia, although he was born in the US. He is super modest and unassuming because he became famous for this. He got to be the president of the Australian National University. And the first thing he did is to ask for pay cut because he thought he was being paid too much relative to other professors. And I can guarantee you that no other university president in the US or anywhere else would ever ask for something like that. Anyhow, he is just the greatest person. There is an interesting, funny story I wanted to tell you. Apparently, after he got his Nobel Prize, he decided to go to see his grandma in Nebraska or wherever he's from, to show it to her, and he did that. And he goes to the airport TSA security, the bag containing Nobel medal. Of course, it rings. TSA just, what's this? And he said, well, it's my gold medal. Where'd you get that? He said, well, the King of Sweden gave it to me. Oh, yeah, asshole. So after giving him hard time, he thought, was pulling your leg. They finally realized, no, yeah, this guy really is somebody who got Nobel Prize, and let him go. Anyway, they did deserve the prize they got, but it actually wasn't all that new. Over 20 years prior to that, two cosmologists, Jim Gunn and Beatrice Tinsley, who was pioneer of galaxy evolution, published this article in Nature magazine, where they looked at observational evidence then and concluded that it's suggesting that we live in a universe with a positive cosmological constant, because ages of globular clusters and Hubble time did not match. The density was measured to be low. The deceleration parameter from Hubble diagram of galaxies, not supernovae, was suggesting that. And exactly the same reasons, except much better measurement today, are why we believe this is the case. But here they are. From pretty much lousy data by the present standards, they got the right answer. And I have to say that I was always a great fan of cosmological constant ever since I learned about its existence. In fact, my very first paper included data analysis that included cosmological constant. So I can't resist but show you this. So Gunn and Tinsley in 75 and 85 as a grad student, I put this diagram together, which is similar to what you've seen before, which is on x-axis it's matter density and y-axis is vacuum density. The solid curve is flat universe, which is what inflation theory is predicting. Inflation theory is very popular. At the time, everybody said, oh yeah, universe must be flat. And of course, since cosmological constant is zero, it must be critical density of matter, even though all observations said, no, it's not. It's more like a quarter of that. But also age of the universe then depends on the combination of these two things. And if you believe the universe is flat because of inflation, and you believe measurements of density, and two intersect at a point that is, oh, lo and behold, about 30% density of matter and 70% of dark energy, and that gives you exactly the correct ages for globular clusters. So I put this together, and my advisor told me not to show it at the conference because everybody will think that I was a crackpot. Because there was sort of this religious conviction that cosmological constant must be zero. Well, I usually never listen to my thesis advisor, but highly unusually, this time I did. And I never showed it or published it. But this was probably the greatest mistake of my career. Not that I compare myself to Einstein. So I should have stuck down with it. But anyway. Anyway, today we have vastly better measurements of all these things, from supernovae, from microwave background, from clusters, for all kinds of stuff. They're much more precise than what people had in '98. And amazingly enough, all these different measurements using different samples, different methods, even different physics, I mean, sense like gravitational lensing versus kinetic energy, they all converge to this one tiny little circle that sits on the universe, model universe that is spatially flat, that has about 30% density of the matter and 70% density of dark energy. And the reason we believe this is that every single measurement we've done so far of all different tracers, everything, the most precise measurements of micro background, they all agree. And that's why we believe that these things are true. Okay, so what's the dark energy then? It's completely unknown. We think that dark matter is composed of some new kind of particles. They're not in the standard model of particle physics, and that's okay. I mean, we didn't know about all these particles back in 1970s. Now, we produce them in accelerators and all fit in this great scheme of their leptons and quarks, and there are 3 different families of particles and antiparticles, so it all works beautifully. But particles of dark matter are not part of this. They're part of some physics that goes beyond the standard model, which is why physicists are so excited, right? So I think it's only a matter of time before we find out what are these particles. Maybe then we'll learn more and have next stage of particle physics. Dark energy, on the other hand, not made of particles. It is something entirely different. As I told you, it's unlike any other form of energy we know. I suspect it has to do with intrinsic properties of space and time and gravity that we don't know yet. And there are literally thousands of papers published trying to understand it, and at most one of them is correct, probably none. Even I publish papers about this, and I know they're not correct. And the problem is that physicists naturally do what they know how to do. So they just did same kind of analysis they did before, and that's just not going to work. So my guess is that it's going to require new Einstein, a new qualitative change in the way we understand the universe, that we'll see that theories we have now are just limiting cases of a deeper theory, which would explain what the dark energy really is. All right, so that, I think, is all I had to tell you, and now I will be happy to answer your questions. So let me scroll back and look for capital letters question. Well, hold on. 42. Here's one from Phil Youngblood. Kepler's understanding of planetary motion was delayed because of bias in thinking about the universe as perfect, and Einstein's work was delayed because of thinking of Newton's work as dogma. Well, not dogma. It was a phenomenally successful theoretical framework. So do you think we may have a bias that is delaying our understanding of what dark energy is? Yeah, we do, because we only think in terms of stuff we know. Or is it just that we have not united gravity with other forces mathematically, so there is not a complete understanding of all this? That is definitely true. We unified electromagnetic and weak interactions. We're pretty sure we can unify it someday with a strong nuclear force, and we have not unified it with gravity. And in fact, even without all these other forces, we do not yet have a quantum theory of gravity. So maybe that will be a part of the solution, right? But people allow for this possibility. Nobody says, we have standard model of particle physics and it's got to be true. We know it's not going to be true. Someday it's going to be something better. And so these two items, dark energy, dark matter, are levers by which we can maybe go to the next stage. All right, next. From Ilsa, question, get the Nobel and ask for a pay cut? Yes, think the kind of person that does that, right? And he is that kind of person. Also, is a question, if the universe is expanding forever, I have read out that there may be more than one universe. Will it run into another universe one day? Yes, people talk about multiverse, but there isn't one idea of multiverse. There are many. And in some restricted set of them, yes, there is a possibility that two universes that didn't know about each other will encounter each other someday, and there are potentially observable consequences of that. But in most multiverse theories, other universes are a priori not observable at all. So they're just a speculation, because science has to be testable, and they're just not testable. There is a famous mathematician, Roger Penrose, who was actually a teacher of Stephen Hawking, who thought that he saw evidence for this in microwave background, but he's a mathematician and doesn't know from data reduction. People who actually work on that said, no, that's not what you see. So yeah, it's possible that someday we'll see parts of the greater universe that we have never seen before. We know that there are parts of the universe that we will never see because space is expanding faster than the speed of light, and that light will never reach us. But that's the same kind of universe we're in, only just outside of our observable region. Okay, the question from Dali. Most of the slides were not visible to me, perhaps related to the high attendance. Was the lecture recorded? If not, could slides be made available? I think the lecture was recorded. I think Fran used to do that, but I'm not 100% sure
Yes.
if it has not been.
The lecture was recorded.
Fantastic. Okay, so
George, don't miss Android's kind of embedded ponderance according to the Bekenstein-Hawking equation.
okay. According to Bekenstein-Hawking equation for surface entropy of all black hole event horizon, the maximum entropy of observable horizon will be near the maximum. We wonder what it would do to space if the maximum were exceeded. I think space would have to inflate to stay within that boundary. No, not necessarily. However, you are pointing out to an important class of models, which are called holographic theories of the universe, which basically say all of the information that defines the universe can be found on its horizon surface or hypersurface. Personally, of all different theoretical models for dark energy that have been proposed, I think those have probably the best chance of someday leading to a real understanding. But again, what we know about entropy, statistical mechanics, is based on spatial, temporal, and energy scales that are closer to our own experience. And once you start talking about infinite universes, yeah, things may not work. All right. Brioni's question: has ESA's Euclid spacecraft revealed anything yet about the distribution of dark matter? Well, it will. I mean, we already know a lot about the distribution of dark matter from observations we have. It's distributed pretty much where the visible stuff is, except fluffier. Dark halos are extended more than visible extents of galaxies, but on a larger scales larger than galaxies, dark matter is pretty much distributed the same way that visible stuff is. It's just visible stuff is little lights delineating what the dark matter is. Euclid and our future mission, Roman, are going to do much better on this than we've done so far through weak lensing and whatever. And so we're just getting more and more precise measurements. But there hasn't been any fundamental new discovery, and I kind of doubt there will be. Let's see.
Okay,
Sabrina.
Illing, yeah, can you see that some models predict that dark matter might be self-interacting? Maybe you could take that question too, because you didn't put a question in front of it, though.
I don't see the question, but anyhow, yes. Some people said, well, maybe dark matter has particles and antiparticles. In other words, what they call the self-interacting. Maybe. And if so, it will annihilate. And maybe it will produce visible light photons, which I kind of doubt, because everything we know about it has nothing to do with electromagnetic radiation. But people did look for that using gamma ray observations of dark matter dominated galaxies. And only upper limits were put together. But that requires some very special conditions.
Okay, and then she goes on to ask or speculate that could this explain certain galactic dynamics? And what do you think about that?
Dark matter that we know and love explains all of the galactic dynamics. Self-interacting dark matter was a cute idea, has been tested at some level, nothing has come out of it. And I think a priori, it's not likely to produce electromagnetic signature in any case. People talk about hypothetical dark photons. Now there is a concept, but that too is just a pure speculation. Okay, let me go down. Sabrina asks, didn't Einstein posit that gravity as such does not exist, but is a curvature of space-time caused by mass and energy? Well, yeah, I mean, it's not that gravity doesn't exist. It is just kind of caused by this curvature of space-time that is caused by the presence of mass and energy. So in other words, it's a fictitious force. It doesn't make it any less real. The famous thought experiment is if you're in an elevator, you don't see outside, you can't tell whether you're accelerated downwards because you're on planet Earth or because there's a rocket pulling you up at ever greater acceleration, and it feels exactly as if you were in Earth's gravitational field. So that's so-called equivalence principle, but it doesn't say the gravity doesn't exist. It's just that it's not like some radiation that is emitted from masses. It is due to the mass and energy changing the geometry of space. Bell asks, Dr. Curious, call me George, please. How does dark energy required to explain the acceleration of the universe reconcile with Einstein's cosmological constant and the energy density predicted by quantum field theory? Well, those are two different things. It does fit just fine in expansion of the universe if you actually work out Friedman equations. It does contribute mass, but it has negative pressure. And when you actually solve the equations, it will be accelerating universe. This is why I said it's actually working like anti-spring. It is expanding the space. And dark energy in cosmological constant is a special case of dark energy that is constant in time, which as far as we can tell is the case. All measurements so far suggest that it is really constant in time between here and microwave background. There's some recent measurements from a large survey called Dark Energy Survey that suggest that it might be changing slightly in time, but it wasn't statistically significant result, and my guess is it will go away. But maybe not. Maybe we'll find out. It is changing in time, in which case we'll have another handle on what it could be. Energy density predicted by quantum field theory. Well, that's what I referred to earlier from Zildovich's proposal, where it says there will be such a thing, but we can't compute the level of it was. Incidentally, this is exactly what inflation theory was all about. Inflation theory postulated that in a very early universe, when it was about 10 to the minus 32 seconds old, physical vacuum underwent quantum transition from high level to lower level, and that released vast amounts of energy and expanded the universe exponentially by many orders of magnitude. But what you know in quantum mechanics is if you know that something is a ground state of a given physical system, you don't know how much that state is. And if you know that we can measure its energy level, then you don't know it's a ground state. So, okay, Iling asks, this failure to find wind...
Android, wait a minute, George. Android reposted his question about self-interaction requires that antiparticles will exist? Just above it.
Okay. Yes. Yes, self-interaction does require that there'll be antiparticles. Well, can be just dark matter attracting, repelling other dark matter. Well, it does by gravity, that's for sure. But, I mean, acts as if it's subject to gravity, including its own. But that's not a new interaction. All right, Illing's asking, failure to find WIMPs, which by the way stands for weakly interacting massive particles, challenges our assumptions that raises the possibility that dark matter could be composed of something very different from what we envisioned. What do you think about that? Well, as I said, there were thousands of models, at least, well, hundreds at least, of completely different types of constituents. At one point, there was a review paper that pointed out that the mass range of potential constituents of dark matter spanned 80 orders of magnitude. Well, now we think it's not that. But there are two major families of particles that people consider, well, hypothetical particles, people consider to be possible constituents of dark matter, and those are WIMPs and axions, which are a whole another story. And there could be yet something else. These are not assumptions. These are just proposed solutions. We don't know yet what it is, but it all acts as if it's some kind of particles that we don't know yet, but they do interact gravitationally and not through other interactions. Okay. Bear asks, does dark energy have virtual particles associated with it like the vacuum energy does? We don't know. So if you extrapolate the vacuum energy from virtual particles, you get wrong answers, or you don't get any answer at all. My guess is that it isn't that it is something that's actually completely different. But I don't know. Nobody knows. So there you have it, guys. Anybody else? Well, if not, thank you for coming. If you haven't joined our Scientians group, do so. That way you will get announcements of future lectures and such. If you haven't explored SIM yet, by all means do that. It's meant to be a pleasant place for geeks like us to interact, enjoy, relax, and there are some educational exhibits. So thank you all for coming again, and I'll see you around at some different lecture.